How are you?
Fine. I would like to recommend that the next. Well, I don't know. Well, I don't want to go ahead, but we have a number of things to discuss, and also Professor Cruz, Dr. Page kindly sent me the recording of your lecture, so I could read your very nice lecture, and I had I have a number of comments, but however for the equation to be clear, I'm preparing a letter in text so that the symbols are correct. And now I couldn't finish it because I had to finish the paper for the proceedings. So the last few days I was completely taken. So, but beginning this afternoon I am available. And if that's okay for you, I would like to send you this letter in text with all the symbols, but copy also to Dr. Page and Dr. Garrett, so that we can jointly discuss. I can tell you that I have Italian type enthusiasm about your axiom because, but I want to tell you in advance, give me a chance to try to prove it. But I believe your axioms includes, for the first time that I know, the includes all not only self-adjoint forces, but also all forces conceived by Newton that are not derived from the potential. Not, yes, indeed, it's a question only of realization of your morphism. And that's what I would really appreciate, not only comments, critical comments, not only from you, but also from Dr. Page and Dr. Garrett, because I believe it's important because it's the first time. It's the first time it occurs in 4 centuries, as far as I know, in a rigorous way. I mean, non-potential forces have been treated many times, but never in a mathematically rigorous way with axioms. And so I must tell you that I'm excited. So,
okay, thank you. But you mean you like I sent to you my text file, my text file for the presentation?
yes,
Do you need that? Yeah?
That would be appreciated. I've used the equation. I copy your equations out of your lecture that I received from Dr. Page. Dr. Garrett, how are you?
Actually, I think we have a completely new member here today. Architect Jacek seems to be joining us. I appreciate that.
Okay, yes. Welcome, Professor.
Yeah, Professor Cruz, if you can send me the transparency, the file, I will appreciate it, and I can be more precise. And
okay.
At your convenience, tomorrow is Thanksgiving, so.
Do you need the latex file, or is enough with the PDF?
Latex will be better for me.
Okay.
So
Okay.
I can copy the equation rather than rewrite them then. Very well.
Okay. Okay. I send it to you.
Should we wait a few more minutes for Garrett Sobczak to show up, or
yes,
shall we continue?
Yes. Incidentally, I would like to support Dr. Garrett's proposal that next week we dedicated the meeting of next week to discussions, because we have a number of issues that should be discussed, if that's acceptable by all. And,
well, I should mention that of course I never had enough time to prepare really what a formal presentation today, so I'm presuming that we also will spend considerable part of this meeting in discussion, as opposed to just a formal presentation. But,
thank you.
As usual, there's never enough time.
Oh yes.
And life interferes with our goals.
Okay.
All right. Well, let me at least just put up the shared screen here for the agenda. I can do that. Let's see, where am I? Let's see. Okay. Okay. I guess this should disappear. Okay, can you see the shared screen okay?
Yes, yes, we can see. Mhm.
Okay. All right. Well, another cup of coffee. Just to say a few words to ARC. It's been a very long time since we've exchanged emails on differential geometry and subject like Shipov and so forth. But I recall those discussions very fondly, and I have, by the way, taken a fairly thorough look at the paper that you published specifically on Shipov. So I appreciate that. I don't know if perhaps your audio is not enabled. I don't hear any audio from your side.
Maybe he's mute.
Yes, there's perhaps at the bottom of the screen there's a function called mute.
Yeah.
That you.
And now? Now,
Yes,
Okay.
that sounds good.
now it works?
Yes.
Yes? Okay. So I'm still interested in teleparallelism, certainly, torsion.
Yes.
But I was busy with other things for all these years, wrote a book on quantum fractals. And so the book took me 3 years to write. You know how it is.
Yes, of course. But I remember you had some extremely beautiful graphics that resulted from that research. Also, I have received and reviewed, or just read very quickly, a paper of yours that I would mention today, perhaps just in passing, because it was a paper that I think that you forwarded to the GOL conference in August regarding Grassmann algebra and Clifford algebra from very general formulation, which I recall that you had in fact referred to work by Zbigniew Oshevich from about the 1980s period on the same subject.
We have been friends while in Poland.
Yes.
But then he went to Mexico.
I don't have immediately in front of me the paper that I'm thinking of, but I viewed it as a kind of generalization of that earlier work that Zbigniew published. I don't know if he ever really published it, or it was a technical report or something of the Institute that referred to or claimed that Clifford algebra really wasn't necessary. That Grassmann algebra was more fundamental in several respects, and that
oh,
was,
I think that's philosophy.
Yeah,
you know.
Yeah, not so much mathematics.
You take those tools that are most convenient for a given job that needs to be done, right?
Yes. Okay, well, I think we have our quorum. Dr. Sobchak has shown up.
Oh,
and,
yes. Garrett is there, yes.
Yeah,
Good morning,
hello.
everybody.
Hi, Dr. Garrett, how are you?
Very good, thank you.
Dr. Page was waiting for you.
I'm a little late. I
We're
was,
not in a hurry today.
Oh, that's good.
And Dahlia also, Dahlia Cervantes is here.
Hello, Dalia.
Excellent.
Yeah, good morning. Good morning,
Good morning.
everyone.
Hi, Dalia, how are you?
Yeah, fine. Thank you. And you?
Fine. Happy Thanksgiving to everybody.
Okay. Okay.
Yeah.
It's very nice.
Is it
Happy
Thanksgiving in
holiday.
Mexico?
You
How?
don't have it in Mexico.
Do you have the concept of Thanksgiving in Mexico?
No, we don't have it. No.
No.
It's a normal day for us.
Yes, I know.
It's been discredited in the United States as well. I mean, what do the Indians have to be
Yeah.
thankful about when the
Yeah.
Europeans slaughtered
Yes.
them, pushed them off on reservations?
Yeah, I think that's definitely something to say about that. Yes. Okay. Well, Canada being as cold as it is, we've always celebrated Thanksgiving 1 month earlier. But this year it's warm. So it's warm on American Thanksgiving as well. All right, so let's get started. I just wanted to mention that to start with that we currently don't have any meetings scheduled. No one has come forward with a specific proposed topic, and I know that we're all rather busy in relationship to the GOL proceedings and so forth. So we could at this point decide to suspend meetings for some period of time, or perhaps as Dr. Santilli suggested, we could dedicate time simply to discussion of various topics that we've dealt with over the last few months.
That was Dr.
So I'm-
Garrett. That was the Dr. Garrett suggestion in the
Oh.
past meeting, which I second. Yes, indeed. Yeah.
Okay. Well, maybe you can think about it a bit during the discussion today or the meeting today, and we can, or if you do have some specific proposal, I think that would be, I would be very glad to hear it, to see it. So I'll make the usual announcement in sometime over the next few days if we change our strategy. What else should I say? Well, basically, I guess we start with presentation. As I mentioned earlier, I really haven't had time to prepare nearly as much as I wanted to. But the motivation for what I wanted to say today, and hopefully we can discuss it in more detail, or in relation, in fact, even to some of the other presentations we've had this fall, is mostly a response to Garrett Sobchak. I think in the very first meeting, Garrett, you said, well, you wanted to discuss covectors. Like, why do we need covectors? So from the point of view of Clifford algebra, of course, we don't even really think about the subject as such, or at least not in any fundamental way. And I remember from your presentation, Garrett, that you started by saying, well, let's just assume Euclidean algebra. I mean, that's basically that's the starting point. And I asked the question at the time, I think, of sort of what you mean by geometry, Euclidean geometry, and it. I don't know if we had a specific answer. It was more a matter, if I don't want to put words in your mouth, but I think you have at least in your comments you made me understand that you consider it intuitive or foundational, that one should understand that geometry is something that almost that we're born with, or at least that we learn at a very early age in mathematics, to the point of being something that we don't need to ask any more questions about. Of course, maybe that's overstating it. I mean, because of course, questions of curvature and Riemann geometry and so.
Yeah, my main idea is that we should extend the real number system to include the intuitive concept of direction, which we know from vectors, planes, planes of lakes and
Yes.
so on. And yeah, I'm not so since Clifford algebra is really isomorphic to matrix algebra, there's all kinds of interpretations for all kinds of geometries, depending upon what you call a bivector. A bivector can have square plus 1 if it consists of a space-like vector with the outer product of a time-like vector. So there's just many different types of interpretations. So the idea of a metric, to me, is not so critical as most people. When you talk about a covector, okay, well, covector is just a mapping from vectors to scalars. That's all it is. I don't see it as any more fundamental. I agree with Professor Jacek on that. It's just a philosophical point of view, really, than anything more than anything else.
Dr.
Well,
Garrett,
I mean,
yeah, Dr. Garrett, remember our discussions on the ISO unit as being, as visually unrestricted. There is no restriction as, no impediment as to, for the interpretation of the ISO, or I should say the realization of the ISO unit as being a vector. Yes, which means all number becomes vectors because they are multiplied, they are ordinary, ISO numbers are ordinary number multiplied by the ISO unit. ISO unit is a vector, so the whole numbers becomes vector in this case. And
actually, I've been looking at your definition of an ISO polymatrix, and that's where actually the geometric interpretation becomes very interesting. And in fact, we can talk more about that sometime, perhaps, what you mean by an ISO polymatrix. Very interesting, really.
Is to add, to maintain the spin 1/2 for a proton and neutron in a nucleus, but at the same time add those a degree of freedom which has been missing for 1 century. It has been quantum mechanics has been unable to represent the magnetic moment because of because apparent deformations or alteration of the charge distribution of those particles, and those have to be represented necessarily. There is no other way that I know. Without changing the spin 1/2, which means changing everything, Pauli principle, etc. So there is no other way than to do it via David Bohm, by embedding David Bohm hidden variable in the very definition of Pauli, the structure of Pauli matrices. That's the main idea.
Yeah, well, I've actually just been thinking about that the last couple of hours, and it's very interesting. I think there's much to be said what you can do by interpreting it as a mapping of Clifford geometric numbers onto Clifford geometric numbers in a different way. It's, for example, normally if you take a frame and you rotate it with a Lorentz transformation or with a ordinary Euclidean rotation, it preserves the pseudo-scalar element. But in your ISO mapping, it mixes things together in an unusual way, which is, I think, what you're saying as well. So we could explore that idea more too, I think.
I do like to proceed, in some discussion along this line. There were some emails exchanged between myself and Dr. Santilli over the last week, although it's certainly not in as much depth as I would have liked to have time to do. But maybe before we do that, I'd like to step back and if you can bear with me for a little while, most of what I'd like to say at the beginning will sound like philosophy, in at least strategy. And I wanted to emphasize really what Oshevich was presenting. In fact, even in some of his lecture notes for seminars to students in the last few years at FESC, he strongly wanted to promote the idea that one should begin at a deeper level than geometry, in effect. I mean, basically beginning with algebra, or you like abstract algebra, and starting just with the notion of a ring, basically, and then maps on the ring, or functions. Right? So we want to consider the algebra of functions as a very fundamental notion. So this is very much pre-geometry. I mean, this is beginning with something that, as you would call in normal usage, like real numbers or something of that form, and just maps on real numbers. And this is very much consistent with foundational sort of category theory and so forth.
May I make a comment here? Yes.
Certainly.
This idea that instead of vector fields, we should have this derivation of the scalar algebra of functions. There is a whole book, for instance, Helgason book on symmetric spaces, where he introduces differential geometry. His definition of vector fields is exactly as an algebra of derivation of scalar function. It's a standard thing. I mean, there are different ways to approach differential geometry, and this is what you say that derivation of the algebra of scalar function. You start differential geometry with this. Is just one part very well known in differential geometry.
Yes.
Okay.
Yes, I agree. It's very well known, but it's not very widely applied in physics. I mean, and perhaps the discussion that we are having, say, that I indicated with Gerrit Sobczak, was that it was sort of more foundational or deeper in the process of abstraction to begin with the notion of derivations, rather than even before talking about geometry.
Look, there is this generalization of geometry, which is nowadays called non-commutative geometry.
Absolutely, right? Yes.
And in non-commutative geometry, when you want to discuss vector fields, of course, there are no tangent spaces, but there is an algebra and there are derivations. So this is how these people proceed. Yes, so it's more general concept.
Yes.
Yeah, my understanding of Zbyszek, he had to do away with geometry altogether, replace everything just by algebra. Well, but then I refer back to Hestedy's quotation, algebra without geometry is blind, geometry without algebra is dumb, which I think is very apt. I think geometry really gives you insight into ideas.
Well, yes, I wouldn't dispute at all your comment, but I would claim perhaps that that's an accident of evolution, right? That human beings need to exist in the world, and they have, in a sense, built in to the programming in the brain to think in some geometric way, right? To make some analogies that are very fundamental indeed. And I think that is both an advantage and a disadvantage to geometry, right? Because it makes, I mean, the subject of geometry was, like in foundations, it was measuring things, measuring the earth, right? And the point was to do this in a rigorous way, to develop a mathematical system which facilitated that kind of measurement. And so in a sense, it was a encapsulation of something that human beings found naturally intuitive.
Well, yeah, that's where, of course, utility in geometry is very natural. But of course,
yes,
that was discovered as not sufficient when you invented Lorentzian geometry and
well, but that was, and that's fine, and it's not really a criticism of geometry as such, but it's emphasizing that geometry is a mathematical system, right? That it's not a, so in other words, I'd want to state clearly that geometry is not part of physics, that geometry is part of mathematics. And there is this unusual relationship between physics and mathematics, of course, that mathematics is sort of unusually good at for being applied to physics. But we shouldn't be inclined to commit, I guess what I think it was Whitehead who said that there's a fallacy of misplaced concreteness. That is, we shouldn't take things as being real, right? That aren't real, like, so that, or maybe better, that we shouldn't confuse the words we use with the concepts that they represent. You know, so
Well, I think you can say that algebra really is just pure rules, whereas geometry incorporates rules. It's everywhere in geometry as well. I don't make it such a great distinction between algebra and geometry. They're both inventions, if you will, of the human mind, really, how we relate to reality.
yeah, but okay, let's not get off on a tangent too much. But I want to go back to what you said too about the sort of intuitive notion of direction, because I think that from the algebraic point of view, oddly enough, it isn't really clear from the abstract formulation alone, but derivations are a reasonable substitution for the notion of direction. The fact that you need an algebra in which derivations can be expressed is a more fundamental notion of direction than the concept of vector as such.
I think they have the same rules, so I'm not sure you can say one is more fundamental than the other. They obey the same basic rules, algebraic rules.
Well, I just want to sort of emphasize that that derivations are expressed entirely algebraically without any intuition as to what they might mean. But here's another accident in which this particular, Leibniz rule, for example, gives rise to an algebra which is especially good at representing the notion of direction. So that's where you begin with the notion of vector fields, is only after you've defined what you mean by a derivation and how to describe it algebraically. And just to skip the details, I mean, as you said, a covector is a way of measuring vectors. That is a way in which we want to map vectors into values. And so we need to think of, and again, I'm trying to emphasize that thinking of covectors as measuring devices for vectors is again more fundamental in a philosophical way, metaphysical way, than the notion of geometry as such, or for that matter, even the notion of a scalar field. I shouldn't say that, scalar product. So we haven't even really defined what scalar product is yet, but we know that we can apply covectors to vectors and get numbers. So the only missing component here to get to geometry is presuming that there is a mapping from vectors into covectors. And that's exactly what we view the metric as a convention, as a choice, as a way of mapping vectors into covectors. And from that, the rest of geometry follows.
How about an isotopy? An isotopy is a map, a kind of a map. This maybe
an isotopy. Yes,
isotopy. I'll look at it. I'll look at this possibility. Yes,
as an equivalence relationship, right?
Ultimately, there is an equivalence, yes. Also, if you accept the isodifferential calculus and you formulate the iso-unit, realize the iso-unit with a vector, then the derivation is strictly directional, is essentially equivalent, fully equivalent to, well, the equivalence between the derivation and the vectors becomes much stronger in my view.
Maybe this is a good point at which to mention that, or to emphasize that so far, everything I've said has avoided the use of coordinates. I mean, there's no notion of coordinate here at all.
What's your definition of a vector itself?
Is an operator on the algebra.
Oh, I thought that's a covector is an operator, but a vector.
No, a vector is a derivation, right? A vector is an operator that satisfies the Leibniz rule. That's all we need to say about it. Right? That every vector is a derivation. Is a derivation.
But yet we use the language of geometry. A vector is a directed line segment. You know, that's why do you even use the word vector since it's so tied to a directed line segment? I mean,
well, as I said here, I would avoid the use of the word vector. I would say derivation, but people are like, because as you and this is what I wanted to say, like, this is why geometry is bad, right? Because geometry is so foundational that we insist in thinking in geometric terms. It's something that we human beings have built in, right? But really, for the sake of abstraction, we want to try to avoid appealing to intuition, right? I mean, we want to be able to explain intuition, so we want to be able to know why certain intuitions exist and what they're good for. But we don't want to say that intuitive things are the only things that we can choose as foundations. Right? That we need.
So you're replacing intuition with you're replacing intuition with just plain rules, and that's all you can say about it, really. Everything is rules. Okay, well, that's the idea, of course, of category theory. In this article I mentioned last week, you know, is extending it now to infinite dimensions and so on.
Well, yeah, I mean, from a philosophical point of view, I agree with you. I mean, but that's like saying that the world is logical, you know, like that there is such a thing as logic as a foundational concept, and that so logic is sort of not something that we should take just as intuitive, but something that we describe
the problem of quantum mechanics, of course, seems very illogical, but that's part of the basic microstructure that, you know, all kinds of things that come up, really.
Well, yeah, okay, I mean, sure. But where was I going with this? So I wanted to emphasize now the connection that Dr. Santilli, this is what I wanted to comment on in my emails to Dr. Santilli, and that was, there seems to be a close relationship between the notion of abstract algebra in a coordinate-free sense, and geometry in a coordinate-free sense, and the kind of isotopy that you're talking about, Dr. Santilli. And I think the reason why that is, the way that seems to come about, I think, is because there has been a very strong tendency to associate or to think of geometry as physics, right? So to think of coordinates, to think in terms of coordinates first, and then to abstract them second, you know, so we get this notion that a tensor is defined by an equivalence relationship right? And it's the same sort of thing happening in algebra. I think when you talk about isotopy in algebra, is that we're looking for a way to identify different algebras that look only different in a superficial way. So the ordinary definition of equivalence. I think at least when I was doing a bit of background research or references that from your papers, Dr. Santilli, on the notion of isotopy. I think it was Albert, I forget his first name, in the 40s was interested in defining non-associative algebras, and he found that the ordinary notion of equivalence of algebras was not sufficient, right? So he wanted an equivalence relationship on the class of all possible algebras that was more inclusive. And so he introduced this notion of isotopy as a way of saying that one algebra was equivalent to another because under this isotopy, we could map one into the other.
Sorry if I interrupt. Albert merely no word isotopy does not exist in Albert's paper, to my recollection. However, what he did, I think, is something important that will remain in time. Namely, he looked at what is the most general possible formulation of what is the generalization of Lie algebras. And this idea of Lie admissible algebra became very natural. So then the isotopy came later as a mean for identifying all infinitely possible realization of given axioms. For instance, we're talking about the Lie axiom. Then the isotopy allows to identify all possible concrete specific realization that verify those axioms. Back to your question of the equivalence, yes, I do agree, and I believe that this will can be best also illustrated with my rudimentary attempts to understand Professor Cruz's beautiful axiomatization of interaction, which is I call it realization free. And so, which is a synonym of coordinate free. But the point is again that if you consider the professor, we may see perhaps next meeting. You see this abstract, very abstract, nice formulation of interaction, but then you have to look at all possible realization, and that's where the isotopy enters. Or put in a different way, the all infinitely possible realization admitted by the isotopy is equivalent to a realization-free or a coordinate-free formulation of geometry or of algebra. So I agree with you in that sense. I do agree indeed. A very deep connection.
Yeah. So where to go from here? So I have some trouble sort of in relating this to what Garrett is saying with respect to matrix algebra, I guess, because I don't think that the matrix algebra that you're talking about, Dr. Sobczak, really is I mean, you're talking about sort of a concrete realization of matrices, not matrices as abstract algebraic objects, right? Is that correct?
Well, I see. Yeah, matrices, of course, arose after the idea of quaternions and real numbers. Actually, the idea of an actual physical matrix, which has really dominated mathematics for what, over 150 years or 200 years, was actually second to the notion of even Clifford algebra, quaternions and so on. So that came after the geometry of people. I don't really agree with that philosophy that rules are more fundamental than geometry. You know, I think they're on an equal footing. I just don't agree with that philosophy.
I like to make a comment.
Yes,
please.
please.
I think that the idea of Professor Osiewicz was to start with the most abstract formulation of mathematical tools for getting to express the universal character of the physical laws. I think that this was the way that he tried to build the theory in physics, starting from the abstract viewpoint from mathematics. And in mathematics, I think that he finally take the starting point from rings. Because I say the finally because before he uses the idea of manifold many times. But after
he did start out as being very much geometer, right? Being interested in geometry in the most abstract form of geometry at the time.
Yes, but after he wanted to start from ring in the ideas of Dedekind, starting only with the rules of the elements of the rings, and then from this he built the algebra, that in the more general way. Then when we speak about algebra in the more general way, I think that the idea of vector is implicit here. Because we have fields and we have a vector space. And then the idea of vector is the most abstract expression, and those are only relations that are between the ideals of the rings. Then,
but this idea is not naturally in the idea of the ring. Right? The ring is a foundation on which one presumes that one can define like maps or functions, and then you can extend the algebra through Leibniz. Right? So this has gone way beyond the notion of a ring. As soon as you introduce Leibniz, you really have a non-associative algebra. Right? That the way in which derivations enter is not associative. It's
Yeah, I'm just wondering, where does the idea of a finite field come from? You have the idea of a field which arises from, I guess, just counting numbers, 1, 2, 3. But then, well, then of course, yeah. It's
don't get. Well, there is a lot of collision of terminology. So when you talk about fields, you have to be clear whether you're talking about fields in the sense of physics or fields in the sense of mathematics, right? So when you say finite fields, you mean rings that contain only a finite number of elements, but in which that actually form a division algebra, right? So that
exactly, yeah.
Right. So being a division algebra, then you can call it a field, right? Because you only need to have an inverse.
Ideas that arise, characteristic 0, or all kinds of ideas arise. But I don't think should reduce everything just to rules. Actually, the rules really come from, as you say, from our experience of living on this earth. Even the idea of anti-commutativity follows from what bosons and leptons, anti-commutativity arises. Pauli's principle of electrons, you can have spin plus 1/2 and minus 1/2, anti-commutative, but bosons, are commutative.
That's intrinsic. The very notion of interaction is a non-commutative event in nature. Yeah, I agree, Dr. Yes.
Let me just this is a good point at which sort of to pop up this this paper by Zbigniew from the 1980s. This was one that I had referred to, I think, last week I'm not sure if this is one that you're familiar with, Garrett, or not.
Oh, I think I am familiar. That was the first, I forget, yeah, from Grassman to Clifford. Yeah, I talked about.
Yes.
What Zbyszek actually goes over.
And Zbyszek specifically mentions exactly these points that you just raised, right? That the applications that one has in mind here are creation and annihilation operators, and the relationship to particle physics really is where these at least the relevance to physics, like it comes from that fairly deep level.
Yeah, I guess just the idea of category theory alone, which Zbyszek was very interested, the last 20 years, comes from just seeing where rules apply to, the rules itself can apply to many different systems, and therefore, if you abstract, I agree with that idea, but I think that geometry helps give insight.
But from category theory, I think the only thing that really was, like, at least philosophically of interest to Zbigniew was a sort of almost a pre-algebraic view of mathematics. Like, so as a foundational view. So rather than taking say set theory as the foundations of mathematics, he was very much motivated to say, well, we need to take a more abstract type of foundation for mathematics, in which then category theory provides that sort of foundation. So, and very central to the notion of category theory is the notion of morphism, and morphism is exactly what you needed to get this abstraction started, like to get you from rings to derivations. You needed to be able to have a concept of mapping of some sort, and it's artificial in the way that set theory was, like the way that mathematics was presented in the early part of the 20th century. But by the mid 20th century, category theory had shown up, and there was this whole movement of pushing the boundaries, sort of what was, because there were a lot of problems in foundations of mathematics. So you couldn't really, things were not nearly as rigorous as Russell and these guys really wanted, and it was proven that it could not be, right, and through Gödel and
that's right,
so forth.
Right.
So category theory sort of got around that in several different ways by basically by saying that we don't need anything more than the notion of types. We don't have to say anything about that. But we do have to think about morphisms between types and that, anyway, totally. But I don't think category theory is that important here, really. It's only a very general framework, and it's a long ways from geometry per se. So, but geometry, let me get back to that point, I guess. And this was sort of in relationship again to something that Dr. Santilli said in an email, that one of the motivations I think that Dr. Santilli has for talking about isogeometry or iso-Minkowski spaces and so forth was a desire to like deal with this conflict that we have between quantum mechanics and relativity. So that, and I think I agree very much with the statement that you made, Dr. Sindilli, in your email, that most of these problems arise from the acceptance of the idea that the geometry is related to curvature. But this has become almost a, like, how do I want to put this? That to this particular, this is a particularly good example of this fallacy of misplaced concreteness. And it's, in a sense, it's Einstein's fault. I mean, because in the early days of general relativity, it was presented in a very intuitive and appealing way that gravity could be explained as curvature of space-time. But I would very much blame sort of people who misunderstood the point that Einstein was making at the time. I mean, that and it was very, it didn't take very long before people started to talk very seriously about curvature of space. Right? And space wasn't even accepted necessarily as a real thing, right? Like mathematicians and philosophers like Poincaré, for example, insisted that geometry and the notions of curvature and so forth were conventions, that they were part of an elaborate mathematical system. But one shouldn't be confused by this, the power, how powerful this system is and how intuitive this system is. One shouldn't therefore be confused that this actually tells you something about reality. Right? Rather, it's the other way around. It tells you something about the power of the system that you're using to describe reality. And reason why I would say that I wouldn't blame Einstein in the long run is because by 1929, Einstein published another paper during the phase when he was interested in unified field theories that introduced the notion of teleparallel geometry and teleparallel gravitation. And this teleparallel gravitation is completely equivalent. Right? It's a way of describing gravitation in terms of torsion of space instead of the metric. So in teleparallel gravitation, teleparallel geometry, the space is flat. There's no curvature, but instead of curvature, there is a twisting of space. That is, but I should stop saying, like, all the current sort of discussion of this sort of in sort of popular literature insists on saying that this means that massive objects twist space, right? But that's a misplaced concreteness, right? All it's saying is that geometry as a system allows you to describe gravity as in relationship to the metric, but it also the same author of this idea showed himself that you could describe gravity as the twisting of space, as torsion in geometric terms. So this is already clear that there is no sense in which you should deduce from general relativity that gravitation is related to geometry. Like that's just a misplacement of what's real.
So does that say anything about black holes or the?
Well, that's a separate topic, very, very controversial. Dr. Page, I appreciate you mentioned the paper, a 1929 paper by Einstein. As we all know, Einstein tried a grand unification of electromagnetic and gravitational interaction. And he recognized immediately that the grand unification is impossible because of structural incompatibility between electromagnetism and and general relativity when formulated on the Riemann geometry, of course. So, and that paper was precisely on the in the direction that we've been discussing, the two of us. Let's assume
Yes.
Einstein field equation, yes, and Einstein
But of course it's correct that Einstein was motivated to do this because he was searching for a way of unifying gravity and electromagnetism, and ultimately it is said that he abandoned it because it failed to describe electromagnetism. But the long-term consequence of the theory was that it did successfully describe gravitation completely. Right?
Yes.
It was a completely equivalent description of gravity as the one that he started with, where gravity was described as Riemann curvature. But in the end, he was really describing gravity then in terms of Cartan's notion of torsion.
Yes, essentially.
But these are just different applications of an elaborate mathematical system that we call geometry, right? And that the fact that in torsion actually in geometric terms is somewhat more general than curvature when it's applied to gravitation. And in fact, it's a highly researched subject at the moment, that because there are some astrophysical results that conflict on a large scale with general relativity, as expressed by curvature alone. So there are researchers who are highly motivated to look at alternate theories of gravitation that are expressed in terms of torsion, because torsion has some parameters that one can tweak that a curvature-based description does not. And apparently this is, just this year I think there were about 30 papers published on the subject of teleparallel gravitation, for this reason primarily, because they think that it may be a possible way forward to resolve conflicts, astrophysical measurements, conflicts in astrophysical measurements. But I would insist still that this is still an issue of misplaced concreteness, because it's not to say that we should suddenly look at geometry as providing an answer to physics in terms of what is the real nature of gravitational interaction. So I think you have to step back and say, well, you accept, as Professor Guzman is saying, that we need at a foundational level the notion of interaction. How we describe it mathematically is a second subject, but we want to insist that something like gravitational interaction is a physical reality. It happens in nature, and it's something that we need to describe more accurately. But we shouldn't be looking for sort of like magic abstract solutions and then confusing reality with these abstractions. And that's where I say geometry is a problem, because geometry is so intuitive, right? So journalists can say, they used to say that a big heavy object curves space. So you just say, well, take a rubber sheet and put a marble on the sheet, and so you build this intuitive picture, and it's all about Riemann curvature.
The problem,
and it's very appealing. You can tell that to a student, and they think they understand gravity.
Yeah, the problem, however, is that space is, as you said, is nothing. It cannot be it cannot be a physical universal substratum, because that will violate the special relativity for the existence for a privileged system. So experts in gravitation have to admit indeed that space is nothing, doesn't exist. So the question immediately arises: how can something that doesn't exist, nothing of nothing, has such a power to curve an enormous planet such as Jupiter to rotate around. So there are serious issues pertaining. So the effort that has been going recently is to maintain the Einstein field equation, the main conception, but formulated in a different geometry. Geometry which does not necessarily admits the curvature. The Cartan.
So I think your hypothesis that what you call iso Minkowski space is flat, right? I would extend your hypothesis to say, well, that iso Minkowski geometry is teleparallel geometry.
Again, formulated.
So we can.
Yes.
So that we haven't. In fact, that there isn't. Well, I'm afraid that with these notions of isopity applied to geometry doesn't give us anything new, right?
No,
that
your
is,
point. No,
that is something already built into geometry, right?
Well,
Yes.
We're only dealing with models, whatever we're looking at, we're only dealing with our mental models of what you might call physical reality, be it mathematical or whatever the models are. It's not reality, regardless, whether it's Riemann curvature or torsion or whatever, that those are just models, that's all it is.
Yeah, Dr. Page, you're absolutely correct. The iso-Minkowski geometry, by conception, was not being conceived to be a new geometry. No, because it has been conceived to be local, essentially equivalent to the Minkowski geometry. All the effort has been essentially to return to the axiom of a Minkowski geometry, because
equivalent in the sense of being flat.
Yes, that sense of being.
Yes.
But also it's related with the same equation. You just differentiate them with the explicit form of the isotopic element. When the isotopic element is a 4x4 matrix, you have gravitation. When it is unit matrix, you have some conventional Minkowski space. But the geometry is purely Minkowskian. That's the whole effort, is to reduce because in this case you have a guaranteed equivalence between special and general relativity, which is at this moment has not, in my opinion, has not been achieved in 1 century. Unfortunately, I respect lots of work on it, but for me to have an equivalence, I need a method whereby there is a map or a limit in the gravitation and the general relativity that essentially reproduce the Poincare symmetry of the special relativity. This is impossible. Then the list is enormous. Then I want to see a method whereby the general relativity produces the 10 totally conserved quantity at the foundation of special relativity. This is impossible, etc., etc., etc. The only way to achieve it,
I wasn't able to actually find any specific references to a conflict between special relativity and general relativity.
Oh,
in fact, it was my understanding. My understanding was that the whole point of general relativity was to generalize what was done by special relativity. So to be successful at all, general relativity had to be at least compatible with special relativity. That was a minimum requirement as far as.
But even the compatibility is in question. Is debatable.
Well, the usual approach, I think, these days is to say, well, forget about special relativity. Special relativity is just a special case of general relativity. So the real formulation.
Like relativity is a special case of Newtonian geometry, or the other way around, of course.
But I'm sorry.
It remains a special.
Can you repeat that?
The iso-Minkowski remains a special case of the iso-Minkowskian approach. The idea remains.
But there's, in what sense is Minkowski geometry not a special case of general the geometry behind differential geometry behind general relativity? Like, I don't see a conflict there. I don't see
It's not a
any
limiting case.
problems
You're saying
arising.
that
I agree with you that there
special
is,
relativity is not a limiting case of general relativity. I guess you're trying to say that. And I think
Well,
I've seen some conflicts with that too. I guess that's what Professor Santilli is talking about.
I'd like to see some references because perhaps I'm just missing the point. Right?
no, you're not missing the point. It is a very controversial issue as a matter of personal priority. My effort was, my personal effort, that our group is that of achieving is the quantization of gravitation and the grand unification. And the obstacle was curvature. So the efforts were, let's look for some mathematical, I have to insist in the word mathematical representation of gravitation that allows us to achieve a causal formulation of operator formulation of gravity as well as grand unification. And that is allowed by the isomorphism geometry. Yes, it does.
But there are several papers that are precisely on that subject in the case of teleparallel gravity.
Yes, that is no
teleparallel
question.
gravity can be given a gauge formulation, at least a kind of generalized gauge formulation that is analogous to the description of electromagnetic fields, for example.
Yes, absolutely. No doubt about this. Our way is absolutely not the only way. No. And then maybe there are intriguing the interconnection and yes, I agree with you.
But I guess my point that I was going to try to make from this discussion was that one shouldn't be disturbed by Einstein's failure to describe electromagnetism in geometric terms. Like this
No, that was not a problem. No.
Right? And I'm not and I'm not convinced that one needs to generalize geometry as such, but rather I'm much more on the point of view that Professor Guzman is promoting, is the notion of interaction is deeper, is more fundamental than geometry.
Yes, that's what I'd like to address in my email to all of you. Yes, very true.
Yes,
very true.
And I just want to go. Let me tie it back, and I think I'd say, well, it's sort of time maybe for me to stop talking anyway. But it goes back to the sort of philosophy that it took me a while to appreciate, was the difference between Oshevich's view of relativity and the conventional view of relativity. It took me a while to appreciate that when he talks about binary relative velocity, that is, relative velocity between two bodies, he means that relative velocity to be concrete, right? To be a mathematical, to be a physical part of reality. So that just like matter and mass is a physical part of reality, the relationship between two bodies is described by their relative velocity, and it really is disturbing if you were to discover that composing two relative velocities was not associative. If this operation turned out to be not associative, then that means that there's no uniquely defined relative velocity between two bodies.
Yes.
And Oshevich showed that the conventional formulation of relativity took a very different view, that the point of view was that relative velocity was an observation, something that an observer measured. Right? It was not a physical relationship between two things, but rather the way a third body viewed their relationship. And this is irreducible, right?
What is the relationship between, what is the center of mass between a body that's in motion and a body that's not in motion? How do you define a center of mass for such?
What do you mean by a body that's not in motion?
Well, two two masses that are moving with respect to each other. What's their center of mass? Since the frames are different, usually you talk about rest frames, center of gravity of a rest frame. But if one particle is moving with respect to the other, where is the center of mass? Or two planets moving? How do you determine the center of mass between?
You should introduce a third.
The answer is in part 2 of Oshevich's last paper. Right? That was the whole point of his last paper, was to define a physical definition of center of mass for relativity, relativistic dynamics. And he claimed that really this was his proposal was the first successful definition of center of mass for two bodies. And the reason why he was able to do it was because he first of all solved the problem of what was the relative velocity itself. Like it's presumed that in conventional relativity, it's presumed that we understand what we mean by relative velocity. But in fact, this presumption, which dates back to Lorentz and Einstein and so forth, is wrong, right? That the relationship between two moving frames is not described by velocity. It's described by Lorentz transformation, and Lorentz transformations, the parameters for Lorentz transformations require 3 bodies. It's not sufficient to parameterize Lorentz transformations if you have only 2 objects.
You need a third reference, inertia.
And so that's why Oshevich insisted that you have to get rid of Lorentz transformations. That was a mistake early on in the theory of relativity, and it's actually both the solution and the problem were created by the same person, by Minkowski. Right? In 1908, in a single paper, Minkowski published both the idea that Lorentz transformations were an isometry, and he also promoted the idea of a somewhat subtly different definition of relative velocity that was based on just 2 bodies alone. And it was the assumption was embedded in that paper from 1908 that these represented the same thing. And so historically Einstein rejected Minkowski's idea that it had anything to do with isometry of the metric. Because Einstein's formulation in 1905 didn't even refer to metric at all. Right? It was just Lorentz transformation in its pure, simple scalar form. Right? And it wasn't until he was really seriously interested in general relativity that he was really forced to take a really geometric view. So in a sense, Einstein's early views were really pre-geometric. They didn't have anything to do with Minkowski space or any of that. But it was only later that the idea of Minkowski space as a geometry became embedded into relativity theory in the early days of general relativity. In any case, so that was I don't, I wish that he was here in order to defend this view, because I don't think I can fully defend it in as much detail and with as much enthusiasm as Begna would have. But he insisted, for example, that if Einstein had only known that the composition of relative velocities was not associative, he would have abandoned it right at the beginning. He would never have accepted Minkowski's formulation, geometric formulation of relativity, so that was Oshevich's whole point of view, was to try to pare the geometry away and get back to the algebra and describe the physics. Like, don't look to the geometry to give you the physics. but rather to see, what the physics was first. But still you want to do it in a rigorous mathematical way. And so the only way that I could imagine, the only way forward, I think, was as Jesus said, was to begin with foundations that were so deep that they were not really disputable, that they were just, or Garrett, you would have said, well, they're just rules. Right? But you're looking for a system of rules which doesn't tie your hands down to being just what's intuitive. Right?
No, consistent system of rules. But that interesting question then is, if you have, say, two planets that are moving away from each other, where does a third body have to be where it is balanced off and doesn't move?
Yes, and that is exactly the answer that's given in Milshevich's second part of that paper.
So it seems
I
like
think
there should be an experiment to validate this idea then.
Absolutely. Like he was very strongly motivated to look. I mean, although he was he hated to view things as being constrained by experimentation, right? So he said, well, imagination first, right? So first you do the thinking about the problem, and then you go back to reality and see, whether this way of thinking is consistent or not with what you measure. Because you can't even
models, and then
but you
experiments.
can't even, his whole point was you couldn't even measure something until you started with a theory, because measurement was part of the theory, right? And that, so you can't go out and just do measurements and think that from the measurements alone you're going to deduce
Oh, that's right. Yeah.
an answer, right?
You're measuring
So,
instruments.
but anyway, so for example, he was very interested in tightly bound binary stars, which present a problem in general relativity right now, right? The best that we can do is numerical simulations of tightly bound pairs in a Newtonian approximations, like in higher order Newtonian approximations. That's the best we can do, and it's because, exactly like you said, that we don't have a fully consistent notion of center of mass. That the only notions of center of mass in relativistic dynamics that we have right now are deficient in various ways. I mean, some are good and better than others in terms of what they represent, but none of them are fully consistent, and none of them are fully local, right? So that every definition of center of mass in the current relativistic dynamics require you to take a non-local view of the system of interacting bodies, and that's not desirable. Right?
I think that the idea of center of mass take to us to the to include a third observer.
You think it necessarily requires
necessarily.
A third, yes, absolutely. An externally inertial third inertial reference frame.
Yes. Mm-hmm.
You cannot do it without a third. You cannot define. There is not only two. There is no possibility of them consistent definition. I agree, Professor Cruz. I agree fully.
Yeah. So this would be perhaps my homework over the next year. So I've spent most of the last 2 years dealing with part one of that paper. I'm trying to. I should try to bring up that paper because it's. Let me find it here. Okay. Yes, this is. Okay, so this is from the bibliography from the draft of my paper for GOL. And here, let's see, where's the reference? Where is it? Oh, I'm sorry. It's fairly important. If I should just jump back to the first reference here. This one, 9. Yes. No, that's not the right one. Oh, here it is. Yes, this one. Center of mass for finite light speed. Let me just bear with me for a minute, and I'll just jump over to the right place for that. Yes, so this paper, Center of Inertia for Groupoid Dynamics, I think this is a there are different versions of this paper, because I think there was an oops, sorry, this is didn't want to do that. This paper was very much a work in progress, and there were earlier. Let me see if I have the right one. There was a particular version of this paper that was published, and that's the one that just was supposed to be popping up here, but it didn't. Okay, where did it go? Oh, I've got too much stuff sitting on my screen at the moment. But let me see if this is the one. I'm just having trouble pointing to the correct place, because this one. No, this. Well, this paper does have a lot of the details of center of mass anyway for two bodies, and his whole point is that it depends on velocity. So it depends on the relative velocity between two objects. So the center of mass as an object, as a fictitious object, is dependent on the velocity, relative velocity of the two bodies. So it's not. Well,
Yeah, so where would the third body have to sit where it's balanced off between the velocities between the bodies?
and I'm sorry.
Where would that third body have to be so it balances off and doesn't move from where its place? What do they call that? Where a stable position where the two bodies are moving away from it.
Well, it can be an observer. The observer will be the third body.
Yeah, exactly.
Yes, exact.
So there should be.
But if the whole thing falls apart, though, if you insist that you need the observer in order to define the relative velocity, then the relative velocities are no longer unique.
Well, where is the rest frame of the test particle between those two bodies that are in relative velocity to each other?
There is no rest frame, right?
Why not? Each body
there are many different rest frames, right? There's a rest frame there's a rest frame with respect to the first body, and there's a rest frame with respect to the second body.
Well, for the test particle, what inertial system is that test particle in that measures in center of mass?
particle has its own space, right?
Its own inertial system. It lies in an inertial system.
I think that the idea of inertial system is a hypothesis too. Yes, because you need to define this for the formulation of the laws of physics. And then there is one hypothesis here that you put some kind of rules for defining this kind of system. And how Newton says, no? Not external force, then the system is
very
not.
Interesting, very interesting.
But
idea.
you can actually achieve, I think, what you need by realizing that the time-like vector field that describes a body has a well-defined exterior derivative, right? So that this means that you can take the point of view of fluid dynamics, basically, and that inertial systems are defined in terms of vorticity. I don't know if I'm sort of skipping too much, perhaps, but it relates back to what Dr. Santilli was saying, is that one should not treat material bodies as points. Material bodies aren't points in any sense of the word. That they are like little bits of fluid, little things that have some extension, and this extension means that they are described by fields, and these fields have fluid-like properties, like vorticity and so forth, and that the inertial frame associated with the body is just saying that the vorticity of that body is zero, right? That it's not rotating with respect to itself, in effect. But it's something that you can define with respect to that body alone, provided that you realize that the body is described by a field, not by a coordinate in space. Is that, I don't know, maybe I'm...
I have a question. Is that Professor Rosevich said the space of places, or places of a space, the reference system? Or is something connection?
Could you explain your question a little more, Dalia?
Yes, my question is that the reference system, I'm not sure, but it's that for the Professor Rosevich called the space of the place, el space to place, or something like that in Spanish.
Yes.
Es the conserve,
Yeah. Well,
de los lugares, del espacio de los lugares.
In Ostavich's formulation, he would insist that a material body is described by a time-like vector field only. But with respect to that vector field, we can define the kernel of that field, right? And so this is the every vector which is at rest, like describes how should I say that? I have a picture, actually. Let me just jump down. No, that's not the picture. That's not the right one anymore. Let me get my graph back. Which one is it? It's this one. Yeah. So there's a whole series of stuff here that I'll skip. but ultimately, in the algebra that Olszewicz is talking about, you can define two operators. One that is a derivation on the space, and the other one which is an algebra map on the space. So the derivation on the space is the one that gives rise to things like relative velocity. But the algebra map is the relationship between the body in abstract and its space of places, right? So it's is that clear? And I have a picture here somewhere. Okay, that's not that one. Oh shoot! And I didn't really get to talk about what I really wanted to talk about. Maybe was that back when I said that geometry was just vectors and covectors and the isomorphism between them. Then I wanted to extend the notion of what was a material body. So a material body also has associated both a time-like vector field and a covector field, which the covector is the clock that measures the time-like vector, right? So this to complete the picture, right? One needs covectors in order to describe what you would otherwise call a clock in special relativity. That's jump that around. But now, where's the? I do have, or did have, a picture somewhere. That was, oh, jeez. Oh, this one, yes. Okay. This was the picture. This is the split of event space into a time-like foliation and a place-like foliation, right? So this congruences are form the places of a body X, but these are all relative to a single body. So that we only have the notion of place relative to an object. We never talk about rest frames in abstract. We always say, the part of the universe that's at rest with respect to a given body. So that this is
the left one
important part.
are the vectors, and the right one are the covectors.
No, the right ones are the time-like. Well, not to say that. The kernel of the vectors is what's being talked about on the right-hand side, but on the left-hand side we're talking about the subspace. Maybe not, subspace is wrong. It's a quotient of the event space. So it's a set of equivalence relationships on the space of events. So they're equivalent in the sense that they take place at the same place. So you can talk about like the history of New York City, right? And you think of New York City as a place, right? But New York City is being described as the set of all things that ever happened in New York City and the sequence at which they happen, right? So it's this congruence of everything that happens that composes the place New York City. Maybe I'm struggling. Is that
X is something like a conserved quantity or property?
Place is the conserved quantity here.
Yeah.
For X.
Like New York. Mm-hmm. the city.
Yeah, so that's the part that stays the same, right? That's why we can call it New York, right? Is because it doesn't change. But that's not exactly correct, right? That it all changes in a consistent way, right? So it's so that the Oh, okay. I think it's time that I should stop here. We probably have gone a long time past. Well, an hour and a half, I guess. So it's not too far past. I'm sorry to end up on a sort of a confused note, and that's probably the result of just not being sufficiently well prepared. And but I do believe that this algebra that was presented in the introduction to the paper on center of mass by Shevich, which was the last version of which unfortunately I didn't pull up here, but I did refer to it in another place, and I can give you a better reference for it in an email. It introduces this algebra that I was trying to present as an alternative to geometry. Basically, I wanted to argue that this algebraic formulation of Shevich's, which is basically an extension of Grassmann algebra. But
Would you
with
mind to show
particular
the?
emphasis.
Would you mind? Please show the basic equations if you don't mind.
Basic equations of
Odzevich formulation that you mentioned. I think they are contained. They were contained in your yeah, they were,
yes.
in your
Okay,
own
let me.
in your own transparency.
Okay, let me skip forward. It's usual. These things are all too long. Okay, so the first thing one deals with is basic operations on the algebra. Right? So, but the actual equations that
I
we're
think that
interested
is
in,
the tensor product of the
perhaps these are the ones that you're referring
of the
to.
map and the
The map and the derivation.
and the derivation. Yes,
Yeah.
I think this is the principal.
These are both defined in terms of the time-like vector and a clock. Right? And so these two mappings both come from the fact that a material body owns a time-like vector and a clock. And if you have a time-like vector and a clock, then you can define a derivation, which is like derivations on the Lie algebra. So derivations over the Lie algebra come from the D operator, but there is a map operator as well. So you can map the Grassmann algebra of space-time into the Grassmann algebra of space, or is better to call it the Grassmann algebra of place, right? Because this is the quotient of the larger Grassmann algebra that preserves the notion of place for a given body, right? So you could think of this product structure as giving you time and space from space-time, and like but one shouldn't think of it as being given space, because space doesn't exist separately. It's only a given quotient of space-time that we treat as if it was space. But these operators are intrinsic. They involve only the operation of a covector on a vector and the evaluation of some object with respect to the vector and the Grassmann product with respect to the clock. So these things, sorry, these operations all are sort of pre-geometric in the general sense of the word. They don't have anything to do with geometry. They're directly related to the structure of the Grassmann algebra. But the Grassmann algebra includes both vectors and covectors and bivectors and trivectors and two forms and three forms and this mapping between them that we obtain from the metric. So the most important result from Mashevich's paper is, where do we go? Let me just go down a little further. Yes, that is this result that showing that the relative velocity is defined in terms of this split of the derivation and the map. So it's this definition. That doesn't look very good, but it's this definition 26, which is probably the most important thing to understand out of Mashevich's approach to relativity, is that this definition of relative velocity is a fundamental absolute concept. It's not doesn't involve a third body at all. And that you can go on to show that this relative velocity is in the space of the observer, of that observer. So so all velocities are in the observer's space. Right? So that's that second result.
May I ask a question?
Sure, of course.
Yes, I'm just asking, is there a possibility that by formulating the two body by an external, third external body observer, whatever it is, and then this external observer measures individually the two velocity of the two objects, is that possible that under this assumption the associativity is recovered in this system of relative velocities?
To the best of my knowledge, any definition of relative velocity that requires a third body will be non-associative.
So you confirm non-associativity?
Yes. And this non-associativity comes directly from consideration of the Lorentz transformations.
Mm-hmm.
So the only way to get rid of the non-associativity is to give up Lorentz transformations in geometric terms. This doesn't mean you give up Lorentz transformations per se, but you no longer insist that they are isometries. Right?
Yeah.
They're no longer form a group, right?
Yeah.
They form a groupoid, which was the whole point that Mashevic repeated many times, right? Is that when you, the structure of the Lorentz transformations is the structure of a groupoid. And if you give up the notion that it has to form a group, then you can recover the notion of associativity. And having done that, then you can define center of mass and presumably the rest of relativistic dynamics in a consistent way.
Mhm.
That was his hope. I don't think he got that far, but he definitely wanted to discuss what he referred to as the Kepler problem in these terms. And this was the main reason for doing that, was to be able to present results on close-spaced binary star systems. It's because we wanted to treat this as a form of Kepler dynamics, but with a new version of what one meant by relative velocity. And it makes the main thing that happens is that the dynamics becomes modified by velocity. So velocity itself, the relative velocity between two bodies, changes their interaction. Right? Their interaction is.
However, my concern is that, from what I know, which is debatable, if there is this issue of non-associativity may be in conflict with the notion, with an axiomatic conception of interaction, because interactions are associative, to the best of my knowledge. So
yes, that's correct. Right? Yes, that if you don't have associativity, then you're going to have a very hard time defining what you mean by interaction.
Exactly. But then the question arises then, if this relative velocity, assuming that this relative velocity is non-zero, then has to be created by an interaction. But then we have a new type of interaction, a basically new type of interaction, which is non-associative, the morphism will not be verify associativity law.
So much better to get rid of non-associativity to start with, because then you don't have this problem.
That's the trend, and accept associativity. Also in nature, we see the nature event in nature are associative, propagation of information, propagation of so that is basically the trend. That's why my question.
And maybe this does sort of go back maybe to taking category theory as foundations, right? Because one of the fundamental axioms in category theory is that the composition of morphisms is associative.
Yes. Yes.
And that's right back at the very beginning. We've said that we fully expect that when we have relative velocities, we will treat them like morphisms, and the composition of those morphisms has to be associative.
Necessarily, yes, but
and so this was an argument that I had with Coxan. Coxan was still he gave a presentation earlier, and I've had some email exchanges with him, and it was very much like my early exchanges with Zbigniew. Is that I kept insisting from early education that one adds velocities, so that you add a velocity to another velocity and you get a third velocity. But the whole notion of addition is wrong, is incorrect. Right? And so the notion of adding velocities in
but the notion of adding velocities are the composition is.
Yes.
Yeah.
You don't add velocities, you compose them, right?
Yes.
So because vectors are operators, right?
Yes.
Right?
Yes.
Vectors aren't arrays of values that you add together like in matrix algebra. Like they aren't like two column vectors. You add one column vector to another column vector, and if you think that these column vectors represent velocities, it's not going to work, right? That this is not what you mean. Hyperbolic geometry is not going to give you what you need, because you need that the composition of one velocity and another, so that is like operating by one velocity and operating by a second velocity, has to be described by a third third morphism, a third binary morphism.
Yes. and only you can make this if you can implement the composition between the other two. And
the only way, yes, the only way you can do this if you have ternary velocities is to have at least one more body, right? So if you have, say, 4 objects connected by 3 velocities, and you compose those velocities in different ways, the only way you can do that successfully associatively is if you have n plus 1 body. So you take n, you always need n plus 1, or you no longer have associative, any way of describing this as some kind of, you no longer have a unique definition of velocities. It will always depend on this choice.
Yes,
And so you're forced. This is what Waszewicz insisted, that if you take Minkowski's route and say that Lorentz transformations form isometries of a hyperbolic geometry, then you're forced into this situation that you need to presume that there is an absolute frame of reference.
now,
There's always it's the n plus 1th frame, right?
But not necessarily absolute, no. But
I think that this can be presented in another way, because if you are one observer and there is another observer and there are communication between them, no? And then you take the measure of one event. And when you take this measure of that event, then you communicate with the other observer. And the other observer made his own measure. Then you suppose that the relative velocity between observers are related with those measures. Then, but you are here making one supposition, and is that you are you can add velocities, because the velocity that you get is the velocity of the other observer plus the velocity that he get. And in this way, you do not need.
But there is a problem, isn't there, Jesus? Because what do you mean by measure an event? Like, so if observer A measures an event and observer B measures an event, what do we know about their operational process, right? So what, like, we don't.
Okay, the operational process.
We haven't said how the A and B can compare their measuring tools, right?
Yes.
Sorry, I need to change my audio here. I'm sorry.
Okay.
One moment.
Yes.
Okay, that's good. All right. Sorry, I have these earbuds and they work fine for 2 hours, but I think that's usually an indication that it's time to stop the meeting because my audio system stops.
it's okay.
But you were going to say, Jesus, and then I think we need to say it's the end of our meeting. But.
Yes, very interesting. Well, that's why I didn't even have any sense of how much time you spoke. I have no, because everything was so interesting.
I'm sorry it was so disorganized. I wish I had more time to organize.
That's our fault because of the many questions, and of course every question asks for other questions. So it was not your organization. No, this is. I think I feel guilty. Dr. Garrett, how about you? You also have a very intriguing question that, of course, had to be addressed. But
your audio is off, Dr. Garrett, Dr. Sobchik. You need the audio. Your audio is disabled.
My audio?
No. Yeah, there you go.
Yeah, I don't regret the extra time. It's all been very interesting. Very happy to.
I admit that I sort of used your comment from an earlier meeting that as motivation, but unfortunately, I'm not sure I really succeeded in addressing the issues that you were raising. But I know that these are long-term discussions that you've had with Oshevich over many years, so I don't expect to be able to provide a convincing answer at this point, maybe. But only I'd like to say only that it represents my understanding of the views that were expressed by Oshevich, and that it. In my mind, only over the last couple of years has it really started to seem to me like a fully consistent system, that I no longer have very many questions about it anymore. I take it as granted. But
well, they're all just models, and of course, even as we understand on other people's models, it doesn't necessarily mean that it's the same because we can have misunderstandings as well.
Yeah, well, science, as he used to like to say, science is subjective. That's the most we can expect from it. But that doesn't mean we shouldn't expose our opinions to others, right? Because the whole point
also science is polyhedric, so there is a certain phenomena normally requires a variety of mathematical formulations. That's the beauty of the complexity of nature. If I may.
I'm sure that Oshevich was one of his motivations for trying to get to the mathematical foundations was in fact an attempt to defeat this nature, this thing about science, right? Is to get to the point where you, if provided that you accept the foundations, you have no other choice. Right? Your only choice is to provide some other type of foundation, in which case maybe you'll have completely different opinions, but if you stick to mathematically rigorous definitions with deep foundations, then you can hope at least to extend your overlap with other people.
Yeah, if well, so Dr. Garrett, just before you came, I was discussing with Professor Cruz that I was very intrigued about this axiomatic formulation of interaction, and I'm preparing a letter that in tech, because so that the equation can be understood, that I'm sending to both all of you, including you, Dr. Garrett. But maybe again the question, Dr. Garrett, proposal that next meeting be just discussion. That will be great in my view, because that's way we can discuss collegially all together the implication of an axiomatic formulation of interaction, which I believe are very important for actual application in physics. It will be nice to discuss them all together in the next meeting, if that's acceptable to you.
I think that would be great. Is by next meeting, do you mean next week or
yeah, next week? Yes. Yeah, the regularly scheduled meeting next week. Also, another.
And you were able to distribute something in advance of that meeting?
Oh, yes, by tomorrow. I think you should receive it by tomorrow. Yes.
Oh, perfect.
Also, there are so many intriguing problems that emerged that I believe, Dr. Page, that out of this next discussion, maybe we can identify the topic for an informal specialized talk. we can then
Okay.
perhaps identify some.
I mean, my objective, maybe in not too distant future, would be to try to present sort of Ushevich's notion of center of mass for two bodies, relativistic center of mass. I think.
Okay, that would be interesting. That would answer my question then.
Yeah, that's certainly
But let's target. I would like to target that for say 1 month or like maybe
excellent.
something like
Very
that.
intriguing, very intriguing indeed.
Okay.
Okay. Well, I do appreciate everyone's time today very much, and
Oh,
so we will meet again then next Wednesday, and perhaps Dr. Santilli, you can lead our discussion on this subject of axiomatic.
I think Professor Cruz will lead because he's the originator of the notion. I am only a number of questions and
detailing those questions is an important,
but we'll do it.
contribution.
Yes. Together, I think we can do much better. Yes.
Okay.
Okay.
I hope that you have a very good rest of the day, and I'll see you next
Okay.
week.
Happy Thanksgiving.
See you. Thank you.
Happy Thanksgiving for those of us who celebrated.
Yeah.
Okay. Happy holidays. See you.
Bye-bye. Bye-bye.
Bye-bye.
Bye-bye. everybody.
Bye.